Oh, okay. Okay. All right. So last time we talked about the short-term existence of solutions to the harmonic maps heat flow. Right. So the idea was you try and write a solution to the harmonic maps heat flow as uh, uh, well, you consider a map between certain Holder spaces, and then it takes values. I mean, the map between Holder spaces, it takes values in a Holder space of, if you like, curves, uh, functions of time, taking values in a space of maps uh, from the manifold into RQ. And then you want a point in the original Holder space which maps to the zero curve, right? The curve which is constant zero. And so what you do is you construct first an approximate solution. So where is this? Okay. Yeah. So first you construct an approximate solution. You have this map P from C2 plus alpha, comma 1 plus alpha by 2 m cross 0, 1 into RQ, going to C alpha, alpha by 2 m cross 0, 1 RQ. P of U is Laplacian U minus del U del T minus trace of nabla d pi at U of du du. Right. So you want, so you're given an initial data f from m to n C2 plus alpha, and you look at f bar, which is I composed with f from n to I of n sitting inside RQ. And now you want U in C2 plus alpha, 1 plus alpha by 2, m cross close 0, 1 RQ, such that 1 U of x comma 0 is f bar of x. So you have the right initial values at time 0. And 2 P of U is identically 0, right? Okay. And what we did is you first construct U naught in this space C2 plus alpha 1 plus alpha by 2 M cross 0 1 RQ such that U naught of x0 is f bar of x, and P of U naught, this is not identically 0, but this is 0 at time 0, right? Yeah. Okay. So this is the approximate solution. This is a solution to a linear parabolic PD, right? Okay. And then what you do is you consider, so this is U naught. And then what you do is actually you consider an affine subspace of the space of the full holder space. So the full holder space looks like this. This is C2 plus alpha. Well, actually, you'll take a 2 plus alpha prime, 1 plus alpha prime by 2, where alpha prime is strictly less than alpha. Okay, so this is the full holder space. We've got this U naught here. And then I'm considering the affine subspace U naught plus X, where X is the subspace U. So let me call this big space, say capital V. So X is the set of Z in V. Such that Z at time 0 is identically 0, and its first derivative, del Z del T, at time 0 is also identically 0. Okay. And then I'm looking at U naught plus X. So this means basically the set of U in V such that, so if I add something which is 0 at time 0, then U at time 0 is going to be identically equal to U naught at time 0, right? And also del U del T at time 0 is going to be identically equal to del U naught del T at time 0, right? Yes? Okay.
Yes, sir.
Yeah, so I'm moving in this subspace. So this much is Z, and this is U equal to U naught plus Z. Is this clear? Where Z belongs to this subspace X, right? So I'm moving so that I don't change the value at time 0, so that I have the same initial value, and I also don't change the time derivative at time 0. Okay. So if I do this, then if I look at the map P restricted to this U naught plus X, to this affine subspace, then it's going to give me it's going to take values so in the subspace Y, so Y is the set of K in C alpha by 2 M cross 0, 1 RQ such that K of at time 0 is identically 0. So this will be alpha prime by 2. Yeah. Yeah. And then the point is that if I look at this map P restricted to this affine subspace, so this takes value in this subspace Y. This V here belongs to Y, okay, because V at time 0 is 0. And if I take P of U0 plus a Z, this also belongs to Y. If Z belongs to X. All right. And then what we got is that the derivative. So this is the part which I didn't do. So you look at the map P of Z, script P of Z is P of U0 plus Z minus P of U0. So this goes from X to Y. It takes the value 0 at 0. Yeah. And the one thing we didn't do explicitly is that this map is differentiable and its derivative at the origin from X to Y is an isomorphism of Banach spaces. So it's 1-to-1 onto bounded with a bounded inverse. Okay. And so by the inverse function theorem, this will map a neighborhood of 0 onto a neighborhood of 0. So what that means when you translate it for the map capital P, that means the map capital P will map a neighborhood of U0 in this affine subspace U0 plus X. It will map a neighborhood here onto a neighborhood here. Okay. Yeah, that's by the inverse function theorem. Is this clear?
Yeah, it's clear.
Right. And so so what we want is that the point is because V at time 0 is 0, we can perturb V to get a W which is 0 in a small interval of time. Right. So we can perturb it in the alpha prime holder norm if alpha prime is less than alpha and strictly positive. Yeah, so if this is C alpha prime by 2, then V at time 0 is 0, right? And then it looks like something. And what we're doing is we're perturbing it to a W, which is 0 up to time epsilon, and then after some time equals, after time 2 epsilon, it equals V. So this curve is V, and this curve here is W, right? And W belongs in a small ball of radius delta around V. Okay. All right. And by the inverse function theorem, so W is close to V in this Holder space, and W is identically 0 for all t in between 0 and epsilon. And then by the inverse function theorem, there exists a z in x such that capital P of u naught plus z is equal to w. Okay. So you put u, the solution we want, to be u naught plus z, right? So Pu is w, and u has the correct initial value. U of at time 0 is u naught at time 0, which is f bar, and Pu is 0 for time between 0 and epsilon. So that means you get a solution for time between 0 and epsilon, right? Is this clear? This was the proof that we did last time. All right.
Yes, sir.
So the only thing I didn't mention
sir.
was why is this derivative, why is this map script P differentiable, and why is the derivative invertible? So that's a little calculation. It's done in the notes. I can do it for you. So what is script P of Z? This is so P of u naught plus Z minus P of u naught. Okay. So capital P has Laplacian minus del del t, that is linear. So the linear map acting on u naught plus Z minus acting on u naught will just give you the linear map. Del minus del del t acting on Z, right? And then you'll get minus trace of nabla d pi at the point u naught plus Z acting on d of u naught plus Z, d of u naught plus Z, plus so I'll just take the minus in brackets here. So I'll have a minus trace of nabla d pi u at the point u naught of du naught comma du naught, right? Okay. Yeah, so this part is nonlinear in Z. This part is fine. This is linear parabolic operator. right? So this part, we have to see when Z is small, right? I want to get a linear approximation to this, right? So I want the derivative of this part. That's the best linear approximation to this. So here, what will the linear approximation be? So I'm looking at the second derivative of the map pi. Pi goes from RQ to RQ. So the second derivative at U0 plus Z, right? Acting on these vectors. So so that is going to be, so I can take the trace outside. So, well, okay, fine. So what I'll get is trace of, so as a first approximation, when I change U0 to U0 plus Z, what I'll get is the third derivative, right, of the map pi. So that will be nabla squared d pi. This is the third derivative of the map pi as a map from RQ to RQ. Acting on du naught, comma z. Okay. So I'll get this. Plus, well, here I have d of u0 plus z, that's du0 plus dz, and du0 plus dz. By bilinearity and symmetry of this second fundamental form, I'll get 2 times trace of nabla d pi. So this is at u0, of du0 dz. Okay. And then the other terms that I have will be, you see, I'll get quadratic terms in z. There'll be a dz term. So that will be a big O of the C1 norm squared. So there'll be big O of C1 norm of z squared. And here I'll have a big O of z C0 norm into C1 norm. Okay, so these will be the error terms. And the point is, these error terms, these are little o of z, the C2 plus alpha prime 1 plus alpha prime by 2. Okay, because these are quadratic. So, I mean, this ZC1 norm is less than this Holder norm. So when I have it squared, this will be less than this Holder norm squared. So that's a little o of this. And similarly, each of these C0 or C1 norms are less than the Holder norm. So the product will be less than this squared. Okay. So this part will be the derivative. Okay. So that implies that dp naught acting on a z, this will be delta minus del t z minus trace of lambda squared d pi at u0 acting on du naught z minus twice trace of lambda d pi at u naught acting on du naught dz. Is this okay?
Yes, sir.
Yeah, so this is L of z, which is a linear parabolic operator, right? Is this clear? Because it has the highest term in the space variable is Laplacian, minus you have del t in the time variable. And then this term, this is 0th order in the space variable. There's just a z here. And this is first order in the space variable, right? Is it clear? So this is a parabolic operator. So by the theorem on linear parabolic PDEs, by uniqueness of solutions, for L implies that this derivative dp0 is 1-to-1, and existence of solutions implies what? That this is existence implies this is okay. So we see from this calculation the derivative of the nonlinear map script P at the origin, it is a linear parabolic operator, right? Okay. And so the uniqueness of solutions for this linear parabolic operator means that this derivative is 1-to-1, and the existence of solutions for this operator means that the derivative is onto, right? Okay. Fine. And L is also bounded as a map between the appropriate Banach spaces. And finally, the estimate for solutions what is the estimate for solutions that we have? So the estimate for solutions is yeah, this estimate that the 2 plus alpha, 1 plus alpha by 2 norm is bounded by this. So here the estimate for solutions is that the norm Z 2 plus alpha prime 1 plus alpha prime by 2. This is bounded by a constant times the norm of LZ, right? Alpha prime by 2 plus the norm of z at time 0, it's 2 plus alpha norm, but this is 0 because we're in z belongs to the Banach space X, which in which Banach space the value at time 0 is identically 0, right? Okay, so this becomes just a constant times the norm of Lz alpha prime by 2. Okay, so this norm z is bounded by a constant times norm Lz. This implies that the inverse of this derivative is bounded. Is this clear? All right.
Yes, sir.
Yeah. So that finishes the proof of this short-term existence. All right. Okay. Okay. So now,
Sir, I just have a question.
Yes.
Why was L bounded?
Okay. Yeah. So that is actually, that follows from the definitions. So, okay. So you look at the terms in L, right? We have to bound the alpha prime by 2 norm. So if I look at Laplacian of z, that involves 2 space derivatives, right? And my z is in 2 plus alpha prime, right? And 1 plus alpha prime by 2. So when basically when I take Laplacian of z, it will be in the space alpha prime comma 1 plus alpha prime by 2, right? So that will be bounded in alpha prime comma alpha prime by 2. And similarly, if I take one space derivative, I'll be in the space 2 plus alpha prime comma alpha prime by 2. So that is contained in the space alpha prime comma alpha prime by 2. And similarly, this term here, this is a linear, this is bounded by a constant times the C0 norm of Z. The C0 norm is bounded by the 2 plus alpha prime, 1 plus alpha prime by 2 norm. And this last term here is bounded by a constant times the C1 norm of Z. That is also bounded by this 2 plus alpha prime, 1 plus alpha prime by 2 norm. Right?
Yeah. Got it.
So that's all. Yeah. So yeah, the boundedness is straightforward. Yeah. Okay. Okay, that's it. So that finishes the proof. So now we're going to go towards long-term existence of solutions. So the main tool for this is something I spoke about at the beginning of the class, which is the parabolic maximum principle. This is going to be the key tool, which will tell us that various geometric quantities, namely the space and time derivatives of the solution, those will not blow up in finite time. So those will stay bounded. And that boundedness of the space and time derivatives will allow us to conclude long-term existence of solutions. So the key for the boundedness is the parabolic maximum principle. So it says if M is a closed Riemannian manifold, so compact without boundary, and U is a C2,1 function on M cross closed 0T to R. Okay. Then if Laplacian minus del T of U is greater than or equal to 0 everywhere. So on M cross 0t. Then the maximum of u over the whole domain, xt belongs to m cross close 0t. This is equal to just the maximum at time 0, u of x0. Okay. All right. So if this is M and we're taking this sort of cylinder, right? This is M cross 0t. Yeah. Then the maximum is attained here at some point here, M cross 0. Okay. Yeah. So maximum is attained here. Is this clear, the statement? Yes? Yeah, is the statement clear? Hello?
Yes, sir. Yes, sir.
Yes, sir.
Sorry.
Yes.
So let me do the proof. So you define un of xt to be u of xt minus 1 over n times t. Then Laplacian minus del t of un. This will be Laplacian minus del t of u plus 1 over n, right? Okay, so this is greater than or equal to 1 over n by hypothesis, which is strictly positive. All right. Okay. Now you let x naught t naught be a point where un attains its maximum. So the set of maximum I'll write as argmax. Okay. Fine. Yes. Okay. So let me call it xntn. Sorry, xntn. Yeah, xntn. So then, if I fix t, then the map x goes to un of x comma tn. This has a maximum at x equal to xn. That implies that the Hessian in the space variable, Hessian of un at xn, this is less than or equal to 0, right? Yes. So therefore, the Laplacian of un at xn tn, this is less than or equal to 0, right? Okay. Yes. Yes. Is this all right?
Yes, sir.
Okay. And if Tn belongs to the open interval 0t, then del t of un at xn tn has to be 0 because it attains a maximum there, right? Okay. While if tn is equal to capital T, then del t of un at xn tn, this is equal to the limit epsilon goes to 0, un of xn tn minus un of xn tn minus epsilon over epsilon, and this is greater than or equal to 0, right? So this is a one-sided limit. So this is because un attains its maximum at xn tn. Right? So un at xn tn is greater than or equal to un at xn tn minus epsilon. Okay, the point is that, if I'm on the boundary of the cylinder at time capital T, then I can't take a two-sided derivative. I can only take a one-sided derivative. Right? If I'm in the interior of the cylinder at time in between 0 and T, then I can take a two-sided derivative in time. And so since I attain a maximum at Tn, the derivative at Tn has to be 0, right? Whereas if I'm on the boundary of the cylinder here, then I just take a one-sided derivative, but un attains its maximum here. So the value here is greater than the value here. So that one-sided derivative will be positive, greater than or equal to 0. All right. So putting these cases together, if Tn belongs to open 0, close T, then what I get is that del T of un at xn Tn is greater than or equal to 0, which implies that Laplacian minus del T of un at xn Tn, this is less than or equal to 0, right? Because the Laplacian is less than or equal to 0 and del T is greater than or equal to 0. Therefore, the difference is less than or equal to 0. But that's a contradiction, right? Because Laplacian minus del T of un is greater than or equal to 1 over n, which is positive, right? Okay. Is this clear? Yeah, therefore Tn has to equal 0 for all n. Okay. And now passing to a subsequence, we can assume that xn Tn, this is equal to xn comma 0. This converges to some x0 comma 0. And since the xn Tn's are in argmax of un and un converges to u uniformly, this will be in argmax of u. Is this clear? Okay, so the maximum is attained at some point x0 comma 0. That's what we wanted to show. Is that clear?
Right.
Okay. Is this all right for everyone? Yeah.
Yes.
Yes, sir.
Okay. So now, once we have this parabolic maximum principle, we can use this to control various quantities associated with the heat flow. Okay. So suppose U is a C21 solution on M cross close 0 open T. Okay. Well, okay, the first thing we can prove actually is the uniqueness. So we can prove uniqueness of solutions to the harmonic maps heat flow. So proposition, if U1, U2 are solutions on, say, M cross close 0 T to the heat flow, such that U1 at time 0 is the same as U2 at time 0. So if they have the same initial value, then they are identically equal. Okay, so we can prove uniqueness of solutions to the harmonic maps heat flow. So the proof is, you consider U1, U2 as solutions to the PDE del U del T equal to Laplacian U minus trace of nabla d pi at U of du comma du. Okay. All right. So consider them as taking values in RQ. Solutions taking values in RQ. All right. So then define phi of xt to be the norm squared of U1 xt minus U2 xt. Okay. Norm squared in Rn. Right? These are vectors in Rn. Take the difference, take the norm squared. All right. So then what we proved earlier is that if I take the norm squared of a vector valued function, if I take the Laplacian of the norm squared, right, this will be twice the inner product of U1 minus U2 with Laplacian of U1 minus U2 plus twice the norm squared of the derivative of U1 minus U2. Okay. Right. This we already proved. And del phi del T will be twice inner product of U1 minus U2 with del del T of U1 minus U2. Right. Okay. So let me look at the heat operator acting on phi. That's the operator Laplacian minus del del T. So this acting on phi will give me twice inner product U1 minus U2, and then I'll get Laplacian minus del del T acting on U1 minus U2, right? Plus this twice norm of d U1 minus U2 squared. Okay. Yes. So this Laplacian minus del del t of u1 minus u2, if you look at this equation, Laplacian minus del del t of u is trace of nabla d pi of du du. So this is going to be u1 minus u2, and then I'll have a trace of nabla d pi at u1 acting on du1 du1 minus trace of nabla d pi at u2 acting on du2 du2, right? Plus this twice norm of d u1 minus u2 whole squared. Okay. So now this difference between these two traces, I break it up into a sum of differences. So this will be twice inner product u1 minus u2 trace of nabla d pi u1 of du1 du1 minus, I'll put in a trace of nabla d pi at u2 of du1 du1. So I've changed this du2 du2 to du1 du1. So then I have to add this term and subtract another. So then I'll have twice inner product u1 minus u2 trace of nabla d pi u2 du1 du1, and now I'll subtract trace of nabla d pi at u2 acting on, so I'll keep this a du1 and then I'll put here a du2. Okay, and then I have to add this term and subtract the last one. So twice u1 minus u2 trace of nabla d pi u2 du1 du2 minus trace of nabla d pi u2 du2 du2, right? Okay, so I've broken up this difference into a sum of three differences. All right, and then I have the last term. Is this clear?
Yes, sir.
Okay, so now what can I do? Now these I can estimate by the mean value theorem, right? So here I'm looking at the same linear map, trace of nabla d pi acting on the same vectors du1 du1, but at two different points, right? At u1 and minus at u2. So this will be estimated by u1 minus u2 into the norm of the third derivative of d pi of pi, right? And the derivatives of pi are uniformly bounded on all of R cube, right? We extended pi to be constant outside a compact, so its derivatives are bounded. And so by Cauchy-Schwarz inequality, this, I want this to be greater than or equal to something, right? So this will be greater than, by Cauchy-Schwarz, minus a constant times, so I'll get here norm u1 minus u2 whole squared, right? Because I'll get one norm u1 minus u2 from here, and from here I'll get another norm u1 minus u2, right? Okay. So this constant will depend on the third derivative of the map pi, but that is bounded. Okay. And then this part, the second term here will give me a minus a constant C2 times norm u1 minus u2 And then here I have a du1, du1 and a du1, du2. So I'll get du1 and then I'll get du1 minus u2. Right. So du1 is bounded. So this will be bigger than minus a constant times norm du1 minus u2 times a norm of du1 minus u2. Right. And similarly, this third term will also be bounded by a constant times norm u1 minus u2, norm d of u1 minus u2. And then I have this plus 2 norm d of u1 minus u2 whole squared. Okay. Fine. And now I can use the AM-GM inequality. So AM-GM tells me I want to get rid of this norm d, this d of u1 minus u2 squared. So AM-GM will tell me that 1 over epsilon A plus epsilon B, right? So half of this, that's the AM. This is greater than or equal to so A squared plus epsilon B squared. Yeah, so this is greater than or equal to AB, right? For any epsilon positive. Yes.
Yes.
Okay. So here this norm u1 minus u2, this will be my A, and this d of norm of du1 minus u2, this will be my B. So this AB is less than this, so minus AB will be greater than minus this. So this will be greater than minus C1 norm u1 minus u2 squared. And then I'll get so minus C2 into 1 over epsilon norm u1 minus u2 squared plus epsilon norm d of u1 minus u2 squared. And then I have the other term outside, minus 2 norm d of u1 minus u2 squared. So, sorry. So this plus 2 times norm du1 minus u2 squared, this will, I can put together that term with this epsilon norm du1 minus u2 squared. So this is greater than, so I'll get some other constant, minus C1 plus 1 over epsilon C2 norm u1 minus u2 squared. And then I'll get plus 2 minus C2 epsilon norm of d u1 minus u2 squared. And for now I can choose epsilon small such that this is greater than or equal to 0 for epsilon small. So the whole thing will be greater than minus C3 times, so this norm u1 minus u2 squared, this is my function phi, right? So finally what I get is that Laplacian minus del t of phi is greater than minus a constant C3 times phi. Okay. So now I put psi of xt to be e to the minus C3t into phi of xt. Then you can easily calculate that this Laplacian minus del t of psi, what will this be? So I'll get Laplacian of this. So this only depends on t. So I'll get e to the minus c3t Laplacian phi. And then I have minus del del t of this, right? Del del t of e to the minus c3t phi. So that will give me e to the minus c3t. I can take common to all the terms, right? And then I'll get Laplacian minus del del t of phi. And then when I take del del t of this e to the minus c3t, I'll get a minus c3, and that with this minus will give me a plus. So then I'll get plus c3 phi. Okay. Now this quantity, this we've computed is greater than or equal to 0. Right? That's what we just got above here. Right? So the whole thing is greater than or equal to 0. And so that implies by the parabolic maximum principle, for all xt in m cross 0t, psi of xt, this will be less than the maximum when psi is 0. So psi of xt is e to the minus c3t into phi of xt. This is less than or equal to the max over x in m of psi of x0, and psi of x0 is just phi of x0, and phi of x0 is 0 because u1 of x0 is identically equal to u2 of x0. So that implies that phi of xt is 0 for all t, for all xt. Okay. So that implies that u1 is equal to u2. All right. Is this clear? Yes? Yes, is this all right?
Yes, sir.
Okay. So that proves uniqueness of solutions. Okay. So there's just 2 minutes left. So listen, after this meeting stops, we'll have to wait another 9 minutes or something before starting a new meeting. So, Orkujit, if you could just mail us when the new meeting is ready to start, then we'll
Yes,
join.
sir.
Okay, thanks a lot. Yeah, okay.
Yeah.
So let's stop this one. We'll start a new meeting after 8 or 9 minutes. Okay.
I have a question.
Yes, go ahead. Yeah.
So in that, so while you were applying mean value theorem to that,
Yeah, let me just share the screen again. Yeah, yeah. Yeah.
yeah. So it was d pi u2, and then so
Yeah,
you
yeah.
got this. So you got this term 2c2 norm of u1 minus u2 and d of u1 minus u2. I mean,
Right.
where did you get each of the terms from?
Yeah, yeah. So look, so the norm u1 minus u2 is coming from here, right? And Cauchy-Schwarz, right? And
Okay.
these two terms, look, that it's d pi is being evaluated, nabla d pi is being evaluated at u2, u2. So this is the same linear map, same bilinear map. The only difference is du1, du1, and here du1, du2. So you'll get a du1, comma, du1 minus u2, right?
Yeah.
From
Yeah,
there,
fine.
you'll get
Got
that
it.
norm du1 minus u2. Yeah,
Yeah.
that's it. Yeah. That's it. And similarly for this other term. Yeah. Yeah, that's it. Okay. So we'll join again in about 8 or 9 minutes. Yeah. Okay. All right, so we've got uniqueness of solutions to the harmonic maps heat flow, right? Using the parabolic maximum principle. Now, we are going to assume that the target manifold N has non-positive sectional curvature. So under this assumption, we'll show that solutions are defined for all time. Okay. So sectional curvature of N is less than or equal to 0. This is the key assumption. Okay. So then let U be a solution on M cross an interval close 0 open T. Okay. So let this be a solution to the heat flow. So then we have the first proposition is that if I look at the norm of del U del T at xt, then this is less than or equal to the max over x in M of the norm of del U del T at x comma 0. So this is for all xt in M cross close 0 open T. Okay. All right. So the proof is you let kappa of ut be half the norm squared of del U del T. Okay. So this was the kinetic energy. So then we saw that del U del T, del kappa del T, this computation we did earlier. Let me show you here. Del T of kappa of ut was Laplacian kappa ut minus norm of grad tau ut squared plus a curvature term, right? Okay. So we got that del T of kappa ut. This was less than or equal to Laplacian of kappa ut because this sectional curvature of N was less than or equal to 0. Right? We did this 2 classes ago. All right. So if you take this to the other side, then you get that Laplacian minus del T of kappa ut. Right? What is this? This is norm of grad tau ut squared minus a sum over ij in a product Rn of dut ei dut ej acting on dut ei inner product with dut ej. Right? Okay, so this computation we've already done. So this term here, this minus this will be greater than or equal to 0 because the sectional curvature of n is less than or equal to 0, right? So the whole thing will be greater than or equal to 0. So that implies by the parabolic maximum principle, right, that the kappa u t of x comma t, this is less than or equal to the max over x in m of kappa ut x comma 0, right? And that proves the proposition. Is this clear? Yes?
Yes, sir.
Okay. Now, so that gives us the boundedness of the time derivatives, right? Del u del t is bounded. Is this clear? By the norm of the initial time derivative. Now, we can also prove the following. So suppose the Ricci curvature of M is greater than or equal to minus a constant C, okay, where C is positive or greater than or equal to 0. So this is true for M compact, right? The Ricci curvature will be bounded below by compactness, okay? So then what we get is that the energy of ut at any x, this is less than or equal to e to the 2 ct into the max over x in m of the energy density of F at x, where u of x comma 0 is equal to f of x. Okay. And so this is true for all xt in M cross closed 0 open T. So this is not quite giving us boundedness of the space derivatives yet. They can grow at most exponentially in T. That's what we're getting. All right. So the proof of this is that you look at the time derivative del del T of, okay, first let me look at this term rather. So you let EI be an orthonormal basis of eigenvectors in TPM for the Ricci curvature. Okay. So reach M at P. Then we had this one term in the Bochner-Weizenbach formula that was the trace of dut star dut into Ricci of M, right? So this was sum over I inner product dut star dut Ricci M of EI inner product with EI So Ricci M of EI is going to be some lambda I EI. And this DUT star I can take to the other side. So this becomes DUT of lambda I EI inner product with DUT EI, where lambda i's are the eigenvalues of Ricci M. So those are bigger than minus C, right? Because Ricci M is bigger than minus C. So this becomes then summation lambda I norm DUT EI squared. So this is bigger than minus C sum over I norm DUT EI squared. And this is minus C times 2 times the energy density, right? Energy of UT. Is this clear? Yes? The energy density is half
Yes,
the UT squared. So this will be twice the energy density. So we get this. And what did we have from before? So note if gamma I is a curve such that gamma I prime of 0 is EI, then capital D del T at t equal to 0, no, at any t, sorry, capital D del T of DUT of EI. What is this? This calculation we've done many times before. This is D del T. So DUT of EI I can write as del S at S equal to 0 of UT of gamma I of S. So by symmetry, this is D del S at S equal to 0 of del T of UT of gamma I of S. So del T of UT is what? This is since it's a solution of the heat flow, that will be the tension field, right? Tau UT at the point gamma I of S. Okay. So I'm taking the covariant derivative of this. So this is going to be nabla EI of tau UT, right? Okay. So thus, what we get is, if I look at del T of the energy density, so this is del T of half norm DUT squared. So the norm squared is inner product of DUT with itself. So when I take del T of that by metric compatibility, this will be twice inner product of D del T of DUT. So this norm squared is actually a sum over I, right? So I can write here sum over I. So the half and the 2 will cancel. D del T of DUT of EI, inner product DUT of EI, right? Yes? Yeah.
Yes.
Okay. So this D del T of DUT EI, this becomes nabla EI of tau of UT. So this becomes sum over I, nabla EI of tau UT, inner product DUT of EI. So this is nothing but the inner product of the linear maps, tau U nabla tau ut with dut, right? And by the Bochner-Weizenbach formula, this is one of the terms which comes in the Bochner-Weizenbach formula, this inner product of nabla tau with du. So this is going to be Laplacian of EUT, right? Minus trace of dut star dut Ricci m, right? Plus sum over ij, the curvature term Rn of dut ei, dut ej, dut ei, dut ej, right? This is by the Bochner-Weizenbach formula. All right. Okay. So you take the terms to the other side. So, and then you'll see that delta minus del del t of EUT, this is greater than or equal to trace of dut star dut Ricci m, and this is greater than or equal to minus 2c E of ut. Okay, so then you just put as usual psi equal to e to the 2ct into E of ut. Then, like we did calculated before, delta minus del del t of psi, this will be greater than or equal to 0, right? Okay. And so by the parabolic maximum principle, psi of xt, that is, sorry, e to the minus 2ct, it should be here. Yeah, and so we'll get that e to the minus 2ct EUT of x is less than or equal to the max over x in m, e to the minus 2c into 0, energy of u0, and that's it. Okay. Is this clear?
Yes, sir.
Yeah, so this is just the max x in m of energy of f. Okay. All right. So that proves this this proposition, and now we can prove that actually the space derivatives stay bounded. So for this, we need to introduce what's called the heat kernel of the manifold M. So M is your closed Riemannian manifold. Then there exists a smooth function called the heat kernel, H. So this will be a function from M cross 0 infinity, taking values in 0 infinity, such that for all f continuous function from M to R, if we put u of xt equal to the integral over m of h of x yt f of y d vol y. Then u is the unique solution to the initial value problem. Just 1 second, I'm coming. 1 second. That's okay. So U is the unique solution to the heat equation del U del T scalar heat equation equal to Laplacian U, and limit T tends to 0, U of xt equal to f of x in M. Okay. So this heat kernel gives us the solutions of the heat equation. All right. Okay. So what we need is for any fact, the fact is for any epsilon positive, there exists a constant C epsilon positive such that h of xyt is less than or equal to C epsilon for all xy in M and for all t greater than or equal to epsilon. Okay. Fine. Is this all right? Yeah. Okay. So now we can prove that if U is a solution on M cross closed 0 open T taking values in N, and then for all epsilon in between 0 and T, there exists a constant C epsilon such that the energy of ut at x is less than or equal to C epsilon times the total energy of F for all T in between epsilon and capital T and X in M. Okay, is the statement clear? All right. Yes.
Yeah, it's clear. Yeah.
Okay. All right. So let me do the proof. So the proof is, so you let epsilon.
Just a small question. So for the last proposition, you got that ut of x is at most exponentially bounded, but here
Correct.
you're saying
We're
that
getting it bounded, yeah. If
yeah,
t is bigger than epsilon, yeah,
yeah,
right.
okay.
We're getting it actually bounded. So it'll be bounded, yeah. It'll be bounded, yeah. As you tend towards capital T, it's going to stay bounded. So that means in any finite time interval, the derivatives, the space derivatives will stay bounded. They cannot blow up in finite time. That's the point of this. Okay, so we're improving on the previous proposition. We're going to use the previous proposition to prove this one. Okay. All right.
Yeah, yeah.
Okay. So let epsilon be in between 0 and t, and let t naught be in between epsilon and t. Okay. So then we're going to define two functions. Define w1 of x comma t. So we'll define this to be the solution of the heat equation. So it's going to be given by integral h x y t with initial value e to the minus 2c t naught minus epsilon energy of u t naught minus epsilon of y d vol y. Okay. All right. So then delta minus del t of w1 is 0, and w1 of x 0 is e to the minus 2c t naught minus epsilon energy of u t naught minus epsilon of x. Okay, fine. And we also define w2 of xt to be e to the minus 2c into t plus t naught minus epsilon into energy of u t plus t naught minus epsilon at x. Okay. So this is for 0 less than or equal to t, less than t minus t naught minus epsilon. Okay. All right. So then, if I look at delta minus del t of w2, right? So again, I have an exponential in t times this function. So that exponential I can take common, it'll stay outside. And then inside what I will get will be delta minus del t of e of u t plus t naught minus epsilon plus So this minus 2c, when I take minus del del t, will give me a plus 2c E of u t plus t naught minus epsilon. Okay. And now, by the previous proposition, this quantity inside brackets, this is greater than or equal to 0 by previous proposition, right? Well, by previous calculation, right? This is greater than or equal to 0. Yes? Yeah, we did this calculation. This is greater than or equal to 0, right?
Yeah.
Okay. So the whole thing is greater than or equal to 0. So that implies that Laplacian minus del del t of W2 minus W1, this is greater than or equal to 0, right? And W2 minus W1 of x comma 0, this is identically 0, right? They take the same value at x at time t equal to 0, right? W1 and W2 take the same value. Is that clear? Yeah. Right. When I put t equal to 0, this W2 of x comma 0 will be the same as W1 of x comma 0, right?
Yes.
Okay. So this implies by the maximum principle that W2 minus W1, this is going to be less than or equal to 0, right? By the maximum principle. So in particular, W2 of x comma epsilon, if I put t equal to epsilon, what will W2 become? This will become e to the minus 2c t naught, energy of u t naught of x. This is less than or equal to W1 of x epsilon, and that is equal to the integral h x y epsilon e to the minus 2c t naught minus epsilon e of u t naught minus epsilon of y d vol y, right? D vol y. Yeah. Okay. So I have a e to the minus 2c naught here. I also have an e to the minus 2c naught here. So I can cancel those and I'll get that energy of u t naught x is less than or equal to integral over m h of x y epsilon e to the 2c epsilon energy of u t naught minus epsilon of y d vol y. And this h of xy epsilon, by the fact that we stated earlier, this is less than c epsilon into e to the 2c times epsilon into integral over m of e of u t naught minus epsilon of y d vol y. Okay. So the whole thing is less than some, let me call it some c tilde of epsilon. And this integral is what? This integral is the total energy of u t naught minus epsilon. And t naught minus epsilon is positive, greater than or equal to 0. And we know that the energy is decreasing along solutions of the heat flow, right? So this is less than the energy of F. And that's it. That proves the proposition. Is this clear? Yes.
Yeah, it's clear.
Okay. Okay, so that's enough for today. So we've got that the first time derivative of the solution is bounded on any interval, and also the space derivatives. The first space derivative is bounded on any interval. Okay. So using this, what we'll show is actually the second derivatives are bounded. In fact, they're bounded in C2 alpha norm. And from that, we'll be able to prove long-term existence of the heat flow. Okay, so we'll do that next time. So for next time, I think what we'll do is we'll use Orkojit's link. He'll email us links for the 3 lectures. Is he there? Are you there, Orkojit? I guess he's not there. No, he's
Yes,
there.
I'm here, sir. Yes.
Oh, you're here. Okay. So Utsav is not there. Okay, Bashar. Okay, fine. So yeah, just
Yeah, I'll
email.
email all.
Yeah, email. There'll be 3 links for the 3 lectures, so that we don't have to wait for that 10-minute gap. So there'll be 3 different links for the lectures. Yeah. Okay. So Orkojit will email you. Okay. So
Yes.
thank you. Yeah, and I'll see you next on Friday. Yeah, Friday 2 p.m. Thank you.
I just have one question. So
Sure.
for long-term existence, there's no extra assumption, right? It's still just
non-positive.
non-positive.
That's it. That's it. Just that's the only assumption. Yeah. That's it.
Okay.
Yeah.
Thank you.
Okay. Thank you.